Okay, so we're doing question 8 of 3.5, exercise 3.5 from the textbook. And we just read through the question. We have 3.45 sample of iron is heated to a temperature of 295 degrees Celsius and then transferred to a 2 kilogram copper vessel containing 10 kilograms of a liquid at an initial temperature of 21 degrees Celsius. The final temperature of the mixture is 31.5 degrees, and we can assume that would be the temperature of all of the iron, the copper, and of this liquid. We need to determine the specific heat capacity of the liquid. Alright, so what we've got here is that the iron is going to lose energy. So we're going to have the heat loss, Q lost, is going to be due to the iron, and that's going to be gained by, there's going to be a Q gain, a heat gain of both the copper and the liquid. We gain they're going to gain, and it's the iron that is going to lose. So you can use our formula MC of iron times the change of temperature of the iron is equal to MC of copper times the change of temperature in the copper plus the mass of the liquid times the specific heat capacity, which we're trying to find of the liquid, times the change in temperature of the liquid. So this is what we are wanting to find, and we're going to need to isolate that. So we can put our numbers in here. We're going to get 3.45 times by the specific heat capacity of iron is 470, so it's times 470 times we have got the change of temperature is 295 minus the final temperature is 31.5, and that equals the mass of the copper, which is 2, times the specific heat capacity of copper is 385. I've just looked up those values in the textbook. You're not expected to memorize these values. Times the change in temperature, and that is 10.5, plus the mass of the liquid, which is 10 kilograms, times C, which we're trying to find, times the change in temperature, which is also 10.5. So I'm going to solve this. I'm going to basically get this. We're going to calculate this one over here, this side over here. I'm going to subtract from that this, and then I'm going to divide the answer of that by the product of these two. So let's just do that on our calculators. I'm sure you have got no problem with doing this. So we're going to get 3.45 times by 470 times by, open brackets, 295 minus 31.5, close brackets, and I'm going to close brackets again, and then I'm going to subtract from that, open brackets, 2 times 385 times 10.5, close brackets, and I get 419,180, and then I'm going to divide that by 10 times 10.5, and we get a value for my C of 3,992 joules per kilogram per Kelvin. Now you can see here I've got three significant figures in all of these, so I should really do these to three significant figures, so that will actually be 3990 joules per kilogram per Kelvin would equal the specific heat capacity of the liquid. Okay, so there we can see the important thing of getting the heat lost is equal to the heat gain, just setting up your equation. It's really very straightforward. I don't think any of you have any major problems with that. Let's go on to this last question of this exercise that I asked you to do. So we have a refrigerator takes 2 hours to convert 2.5 kilograms of water initially at 21.5 degrees Celsius to just frozen ice. So it basically freezes the water. Calculate the rate at which the freezer absorbs heat. So what's happening is that you're going to have the heat lost, or the heat liberated by the water as it drops down. It's going to be made up of two parts. You're firstly going to get for the change of temperature, which is going to be MC change in T, and then there's also going to be heat loss because of the change from liquid to ice. So we're getting a phase change there, and that's going to equal ml, and that's going to be the Q lost by the water, which has to be absorbed by the fridge, which has to be taken out by the fridge, and we can work out the rate, basically the power that the freezer is absorbing that heat. So let's have a look at this. This is going to be 2.15. Specific heat capacity of water is 4180 times the change of temperature would be 21.5 down to 0 degrees, plus then your mass again 2.15 times by the specific the latent heat of water to changing from liquid to ice to a solid, and that value is 3.34 times 10 to the 5. So it's actually quite a high value, that, and that's going to equal to the total Q. So let's just work it out. So we get 2.15 times by 4180 times by 21.5 plus 2.15 times by 3.3 exponent 5, and we get that the heat lost is going to be 902.720.5 joules. That's a code total. Now we get told that it takes 2 hours to do this, so the rate of heat loss is therefore going to equal this value over here, 902.720.5, divided by the time. And we usually always do it in seconds. So that's going to be 2 times 60. That will give minutes, times 60 will convert that into seconds. So I'm going to divide this by brackets, 2 times 60 times 60, close brackets, enter. I get a rate here. Now, all of these are to 3 significant figures, so I'm going to write mine to 3 significant figures. It's 125 joules per second. We could also write that as watts. Okay, thank you very much. So that was the last question I asked you to do.